Okay. Very well. So, do you have the presentazione?
No, sono loro che così sono connessi e fanno direttamente.
Ok, sono tutti online?
Sì, tutti online.
Tutti online, ok. So, everything is online. So,
Thank you very much.
We are online.
Yes,
We can start. Yes.
Okay.
Hello.
Hello, good morning to all.
Thank you.
Non lo so, bisogna chiamarli. Ma chi è Damiano Pirri? Hello?
Hello. Hello, Franz. How are you?
Hi, yes, no, everything okay?
Yeah, everything's okay now from my side.
Sì, però non si vede più niente, non so. Il primo è Porcelli e non c'è. Ha fatto la foto? La foto? La foto? Dove io? Chiamalo un po' Porcelli, dai.
Possiamo anche cambiare cominciare.
E non c'è nessuno sotto la Islam. E sembra brutto, dai, aspetta un attimo, vediamo. Okay, hi. Good morning to everyone.
Good morning.
On behalf of the co-chairs, I'm glad to give a warm welcome to this workshop titled Cyber Intelligence and Applications, and as a part of the International Conference on Computational Science and its Application. I hope you are well. Okay. Organizing an international event has required the help of many people. Thus, I want to thank the program committee and members and the review for their support. Also, would like to thank all authors for submitting and presenting their papers in this workshop. And I remark that all papers have been peer-reviewed by experts in the specific subject area, and the accepted papers will be published in the Springer Lecture Notes in Computer Science series, which is intersected by Scopus, Engineering, Thomson, and so on. We hope all of you will enjoy at this workshop and find this workshop a productive opportunity to exchange ideas. Okay, let's start. And speaker has from 15 to 15 minutes for presentations, including 5 minutes for questions. Please, I suggest all other participants to turn off the microphone during the presentation. Okay, first speaker is Dr. Farsimadan Eslam. And the title is Recurrence Plots-Based Network Attack Classification Using CNN Autoencoders.
Okay, yes, thank you. Let me share my slides. Okay.
Okay, we see your presentation.
Okay, nice. It's okay now? Everything is okay? Okay.
Okay.
Good afternoon. Good afternoon, everyone. Thank you for participating in my talk. As you can see from the first slide of my talk, the title of our research is Recurrence Plots-Based Attack Classification using CNN Sparse Autoencoders. We have done this research with collaboration with Professor Gianni D'Angelo and Professor Francesco Palmieri from the Department of Computer Science of University of Salerno in Italy. Okay, let's start. Let's start with the introduction. Internet is one of the most important inventions of 21st century that has impacted our daily lives, and many people in today's generation rely on the internet for their professional, personal, and social needs and activities. As you can see from this figure, the number of individual users of internet is increasing year by year, but I mean from this figure, but we can say from the using point of view, it is increasing month by month and also day by day. So anyway, in general, the internet users are increasing, and every day is going to be more higher than yesterday. But there are many challenges related to internet and other communication systems. For example, IoT and cellular networks. They produce enormous and diverse traffic data flows. The behavior of network traffic in these networks is highly complicated, related to the factors same as device mobility and network heterogeneity. As a consequence, conventional and traditional network security and management methods struggle to handle the challenges of securing, monitoring, and analyzing the network and data. So one of the most important and critical and complex challenges in these interactive networks and advanced networking technologies is ensuring the security of these networks and applications with new and more effective methods and techniques. Also, according to the 2021 Cyber Threat Defense report by the Cyber Edge Group, more than 86% of organizations experienced at least one successful cyber attack during 2021. So it is so important to enhance the security of communication systems and networks against security issues and cyber threats. As we can say, as we said previously, mainly as people are relying more and more on wireless networks such as cellular networks and Wi-Fi for their daily activities. In this figure, you can see the percentage of the organization that have experienced at least one successful attack is increasing during the last years. So recently, machine learning and deep learning have proven to be highly effective in facing with the network security concerns and have demonstrated the superiority of our traditional and conventional methods. Motivated by the success and effectiveness of these models, this paper focuses and concentrates on addressing attack classification and detection issue in network security through a deep learning-based model with a particular emphasis on autoencoders and convolutional neural networks. Attack detection, prevention, and classification are at the forefront of the information security landscape as organizations and governments look for good and effective solutions to safeguard their information assets from unwanted and unauthorized access. So in this research, we try to explore the capabilities of autoencoders and convolutional neural networks in automatically finding relevant features and the effectiveness of characteristics coming from nonlinear analysis theory arranged as recurrence plots to support attack detection and classification tasks. So we can say the main idea and the main contributions of this work can be summarized as follows. First, a formal description of the overall workflow is provided to investigate how the proposed method from the theoretical and the mathematical point of view improves and affects the feature extraction process. Second, nonlinear characteristics arranged as recurrence plots and the related features extracted using a CNN sparse autoencoder are used to perform attack detection classification tasks. These two are the main important contributions of this work. We presented the proposed approach through three main steps. The first step is determining new nonlinear features from the basic ones. That is, building the recurrence plots using the traditional delay coordinate embedding process. The second step is extracting the more representative features from the recurrence plots. That is performed by employing a CNN sparse autoencoder architecture. And the final step is implementing the final classification issue that is performed by using the autoencoder related latent space as input to feed a fully connected softmax neural network. In this figure, we can see the overall workflow of the proposed method. It's kind of a CNN autoencoder that we used the latent space to feed a softmax neural network for the last classification goal. As, as previously mentioned, and we said, recurrence plots are an invaluable source of information for understanding the most representative and hidden properties of traffic flows and time series. So we employed recurrence plots images to gain significant insight related to network traffic flows using a grayscale for distances, in which white and black colors are used to represent short and long distances. We did not consider individual traffic flows as a sample at a specific time, but at a specific time, we consider aggregates of contiguous samples determined through a sliding window scheme to better capturing the traffic behavior over this time. This sliding window scheme uses two main parameters. The first one is window size, and the second one is offset. Offset is the time delay and the time offset between two windows. In this figure, we can see how the recurrence plots extracted from the basic features based on the sliding window scheme. For doing the experiments, we used real-world traffic features available in the intrusion detection evaluation dataset. We pre-proposed the dataset in order to present each flow as a low-dimensional vector characterized by only 9 basic features, and we reduced all other features, and we used these 9 features because they are more related to the goal we have. Several sliding windows characterized by having different dimensions and offsets have been considered. Finally, we decided to choose 16 for a sliding window dimension and 1, 8, and 16 for offsets. The implementation details of the employed CNN sparse autoencoder are as follows. For the encoder part, we use the CNN, 3 2D convolutional layers with kernel size 2 and 2, activation rule for all 3, padding the same, and characterized by having 18, 8, and 4 filters for these 3 layers respectively. After that, a flattened layer is employed to map the extracted features as one-dimensional latent vectors to feed a softmax neural network. After having built the decoder side using the inverse sequence of the encoding layers, we trained the CNN sparse autoencoder configuration by using Adam optimizer as well as the MAE as loss function for 50 epochs and batch size equal to 64. After that, we fed a fully connected softmax neural network comprising 2 dense layers with 512 neurons for each layer, activation relu for both layers, and dropout 0.5 and 0.4 respectively for these 2 layers. And finally, to obtain the classification results as the probability distributions, we used a third dense layer with 6 neurons and activation softmax as the output layer. Finally, we trained the whole network with Adam optimizer and a sparse categorical focal loss function for 20 epochs, and batch size is equal to 256. This table and also table 2 and 3 in next slide summarize the corresponding classification metrics derived by fine-tuning the whole CNN sparse neural network as a stacked network for 20 additional epochs. As you can see from this table, in all evaluation metrics, same as accuracy, F measure, and so on, we achieved good results for the classification task related to normal traffic and attack traffics. And all of them are more than, almost all of them are more than 99%. This table shows the results related to, sliding window is 16 for all experiments, but this table shows the results related to offset 1. In this slide, we can see the achieved results related to offset 8 and offset 16. As you can see again, at average of the evaluation metrics, all achieved results are considerable, and we achieved good classification results related to evaluation metrics for also offset 8 and offset 16. As a comparison, Table 4 summarized the performance metrics related to the employed CNN sparse autoencoder neural network configuration for each considered offset. In this table, we consider averaged values. Average values for offset 1 is something like the first row for offset 8 is the second row, and for offset 16 is the last row. As shown in this table, the CNN sparse autoencoder configuration achieved considerable classification results for each considered offset value. I mean, for offset 1 or consecutive scenario, offset 8 or semi-overlapped scenario, and offset 16 or non-overlapped scenario. We have obtained an average F measure close to 99% for consecutive scenario and more than 98% for the semi-overlapped scenario, while we obtained as worsening of only less than 1% for the non-overlapped case and scenario. So we can see, for example, for non-overlapped scenario, we have 97% of F measure for this configuration and classification results. Finally, we analyzed the effectiveness of our approach by comparing the achieved results with those derived from some famous machine learning scenarios, same as naive-based, logistic, SVM, J48, MLP, and CNN-based classifiers by considering non-overlapped time windows with offset 16, which is the worst scenario of our approach. As you can see from this table, I can say almost, and in all of the evaluation metrics, our results are better than the results achieved from the other methods, machine learning and deep learning based methods. The best one and the one that we try to focus on is F measure that or results in is more better than the results that achieved from other methods in state of the art. So we can say, okay, we improve the classification results related to the research that have been done before. In this table, we consider the average values related for our proposed approach is related to offset 16, as I said, as a worst scenario, and for others that we have done the experiments via VCA, and it's the best results achieved based on these scenarios, based on these models. As shown in last table, the proposed architecture outperforms other famous methods based on the machine learning and deep learning classifiers by significantly improving the average of evaluation metrics, specifically F measure. It improves once again the effectiveness of the proposed approach and ability of autoencoders that in any application scenario are capable of deriving meaningful features from traffic dynamics arranged as recurrence plots, and therefore achieve excellent classification results, which is the goal of this research. As an example of future work, an interesting future direction could be investigating the effectiveness of recurrence plots and CNN sparse autoencoders for multiple hostile traffic flow detection in federated organization. Another one could be, for example, a combination with other neural networks, not CNN, for example, RNN, LSTM, and others to construct new configuration and new classifiers and test the capability of them in classifying the traffic flow. And thank you for your attention. I hope I didn't exceed the time, and I try to be more precise in terms of time.
Okay, thank you, and congratulations for your presentation and works. I have just a curiosity in questions. Do you think that your approach, your architectures can be used also for other research field, for example, in healthcare, on also in industrial field?
Yeah. Uh, as you know, CNN architectures, the architectures based on CNN have the excellent capability in image processing. So if we have, for example, experiment that will be done based on some images, for example, for healthcare or some other industrial problems, we can use this kind of configuration because they will work in our scenario. They worked on recurrence plots, but for example, for other picture-based scenarios, we can use it because CNN, convolutional neural networks have this ability to process, to do image processing. So I think it will be good to examine this kind of networks. Maybe it will work.
Very well, thank you very much. Okay, any questions? Do you want some questions? Okay. Thank you, Dr. Farsi Madam. The next speaker is Dr. Robustelli. Title of presentation is an association rule-based approach for anomaly detection on CAN bus.
Okay. Hi, good morning. Can you hear me? No?
No.
You hear me now?
Yes.
Okay. Can you see my screen?
Yes.
Okay. Oh. Okay. Good morning at all. I'm Antonio Robustelli. I'm a postdoc fellow of Department of Computer Science of University of Salerno. And today I will present the following work related to an association rules-based approach for anomaly detection CAN bus. Before starting, I will thank my colleagues and professors Gianni D'Angelo and Massimo Fico for their contributions, effort, and suggestions during this work. So, okay, let's start. The first question is why we propose a CAN bus anomaly detector. As we know, CAN bus represents the main communication channel in modern vehicles. So, because it connects several electronic control units which are designed for the optimal management of several driving-related features, such as engine control, anti-lock braking system, advanced driver assistance systems, and so on. So CAN bus works using the controller area network protocol, which is the de facto standard used by many car companies and in general Internet of Vehicles. However, as we know, the CAN protocol has been designed to operate within closed network environments, and for this reason, it presents several well-known security issues and vulnerabilities, such as airbags and ABS-related attacks, tampering, classic networks attacks like DOS and DDoS, lack of device authentications, and so on. And the main problem that is that the exploitation of such vulnerabilities represent a risk for many peoples, for the life of many peoples, like drivers and passengers. And to face the goal of such hostile activities and vulnerabilities, several machine learning and deep learning based solutions have been proposed in the last years. However, supervised deep learning based solutions do not consider new attack typologies. Instead, semi-supervised deep learning based do not accurately detect well-known attacks because they often present a considerable number of false positives and false negatives. And finally, machine learning based ones do not consider the vehicle state over time, but they only perform a simple message by message detection. For this reason, the goal of this work is to propose a novel semi-supervised anomaly detection approach in which we consider the vehicle state over time and we show that its effectiveness by obtaining comparable results with the state of the art solution. In this work, the core of this work is represented by the vehicle state. We can define the vehicle state as the correlations among messages or CAN commands that are sent on the canvas in a specific time interval. And directly, as you can see from the following picture, it means define the vehicle state by considering the correlations among different ECUs working in a real driving scenario. To consider the vehicle state over time, we proposed an approach based on three most famous algorithms that are the cluster-based learning algorithm, the key nearest neighbor, and a priori. The main idea is to build an attack-free knowledge an attack-free knowledge as follows, in which we map each CAN message into a specific region. We find the correlations among such regions. Then we represent such correlations as corresponding associative rules. And finally, we analyze multiple rules using a sliding window mechanism. In this way, we are able to consider the licit or attack-free messages or sequences that are sent on CAN bus. And indirectly, it means simulate a normal operating scenario. More precisely, in this work, we use the CLA algorithm to map each CAN message in a corresponding multidimensional region. As you can see from the following picture, the CLA builds each region by considering the 8 bytes of data field that are extracted from each CAN message, and these 8 bytes are used to derive the centroid's coordinates. In addition, this algorithm employs a lower and upper bounds to consider a sort of admissibility area. This area is important to improve the definition, the accuracy of each region. Then the KNN algorithm is used to consider and extract the correlations among such regions. This new clustering step is important because such step gives the capability of grouping CAN messages that are more correlated among them, but that present a different CAN ID. So next, a sliding window-based mechanism is used to consider multiple CAN messages sent over time and arrange such messages as corresponding associative rules. This step provides the capability of considering the vehicle state over time, which can be expressed as a set of different sent messages, and in other words, rules. However, to consider only the most frequent message correlations and also to improve the detection effectiveness of our approach, we use the a priori algorithm in order to remove only any irrelevant rules. The following picture summarizes the proposed workflow in 5 main steps that we applied for the training and testing steps. Such steps are the kern regions definitions, the kern regions clustering, the rules mining training, the rules mining testing, and the item sets checking. More precisely, we formalize such workflow by defining 2 algorithms, one for training and another one for testing. The training algorithm is responsible for to the kern regions definitions, to the kern region clustering, and finally for the rule mining training. More precisely, such algorithm provides as output the list of most frequent item sets and the clustered regions. Such 2 lists are used by the testing algorithm to detect possible anomalies or attacks. Then the testing algorithms is responsible to the rules mining testing and finally the item set checking. The last step, the item sets checking, is important because it provides the detection result data set, that is the data set containing the detection results. So to show the effectiveness of the approach, we use the care hacking dataset that is one of the most famous dataset related to CAN-bus anomaly detection. It consists of 5 CSV files or dataset that are GIDS, containing only attack-free CAN messages, DOS, fuzzy, GR, and RPM. More precisely, each file reports around 30-40 minutes of observed traffic, and for the training phase, we use only the attack-free CAN message. And then we use only for the training the GIDS dataset. Therefore, we employed the sliding window-based approach using the following parameters. For example, we consider 300 centroids for the CLA algorithm, 50 clusters for KNN, a sliding window containing 900 messages, and as a sliding window offset of 4,100 sites, and a support value for the a priori algorithm equal to 0.9. However, due to the huge quantity of data derived by the KNN in terms of number of rows and columns, we applied an additional quantization step. This step has been applied in order to reduce the dimensions of the dataset. And for this reason, the next step related to validation and testing has been done by using this derived dataset. After that, we validate the dataset by using only the licit CAN messages, and to accomplish this, we use the key-fold cross-validation algorithm with the 6 folds. And as you can see from the following tables, we achieve all the best metrics for each considered metrics that are accuracy, precision, recall, and F1 measure. and we can appreciate that no false positive have been detected. This information is important because it provides a first proof of effectiveness of this approach. After that, we test the effectiveness of our approach using the remaining 4 data sets that are DOS, fuzzy, GEAR, and RPM. And as you can see from the following table, we test the effectiveness of our approach in detecting normal or attack-free CAN messages and attack CAN messages. The first table is related to normal CAN messages. Instead, the second one is related to attack CAN messages. In both cases, we achieved an accuracy around 99.47%, and also we achieved always excellent values for the other considered metrics that are always measured than of 99%. Finally, we compared the approach with the most notable machine learning-based detectors. And as you can see from the following table, the proposed detector achieved statistic metrics totally comparable to those derived or related to the most famous machine learning-based solutions. However, as I told before, they are not able to consider the vehicle state over time and then the correlations among multiple electronic control units. So, in conclusions, we proposed a semi-supervised approach to detect CAN-bus attacks. To accomplish this, we propose and consider the vehicle state over time by combining 3 most famous algorithms and a sliding window mechanism. And finally, we prove the effectiveness of our approach in detecting licit and illicit CAN messages with an average accuracy of 99%. Also, we compared the effectiveness of the presented approach with the most notable machine learning-based detectors. Finally, we would like to propose the following 2 future works. First of all, we would like to employ the proposed detector to spot new anomalies and attacks in related to CAN-bus or Internet of Vehicles. And then we would like to propose to use the proposed approach in other application domains in which the correlations among different features can represent and play a very relevant role. So I finished my presentation. Thank you for your attention.
Okay, thank you for your presentation. I have just a question. Do you think that this approach can be used for implementing the federated learning?
Yes, because we can see the correlations among different vehicles, coming from different vehicles as important distributed data sources that are used for their nature in a federated scenario.
Okay, perfect. Thank you very much for your presentation. The next speaker is Dr. Porcelli. The title of the presentation is Mitigating User Exposure to Dark Patterns in Cookie Banners Through Automated Consent.
Hello, can you hear me?
Hello. Okay. We don't see your presentation. Okay.
Yes, just a moment.
Perfect, I see it.
Okay. Good afternoon, everyone. My name is Lorenzo Porcelli, and I am a PhD student in computer science. Today, I'm going to talk about our paper called Mitigation User Exposure to Dark Pattern in Cookie Banners through Automated Consent. Informally, our goal is to improve how users interact with the cookie banners, as most of them encourage users to accept all cookies in a misleading way. In the past few years, there has been a continuous exchange of personal information without much interrupt. It was only with the introduction of the GDPR that privacy problems related to online services started receiving more attention. The most visible consequence of GDPR is the appearance of cookie banners. In fact, in order to comply with the GDPR, websites need to show notification asking for permission to use cookies. The main approach used for gathering user preferences is the Transparency and Consent Framework, which was created by Interactive Advertising Bureau. This framework is recognized as the only GDPR consent solution built by the industry for the industry. It involves several stakeholders, including publishers and consent management platforms. Publishers have websites that users visit. Consent management platforms instead collect and manage user consent. Let's consider a simple scenario with user X, publisher 1, and one consent management platform, and see what happens under the Transparency and Consent Framework when a user visits a website for the first time. It's important to note that according to this framework, users are expected to set their preferences every time they visit a website. When the user reaches the publisher's website, the publisher uses a JavaScript code to connect with the consent management platform. Then the code of the consent management platform runs on the page and verify if a transparency consent string, a TC string, associated with the publisher 1 is present on the local storage of user X. The TC string is used to store, update, and modify a user consent in a standardized manner. Since this is the first time user X is visiting publisher 1, no corresponding TC string is found. In this situation, the consent management platform shows a cookie banner on the website. Next, the user selects their preferences on the cookie banner for each specific purpose. The consent management platform then generates a TC string for user X publisher 1 by encoding the consent information. The publisher stores this string locally on a device of user X. Later, the publisher can use the API of the consent management platform to decode the TC string and understand the specific purposes for which user X has granted consent. This framework seems to work. However, there are several problems related to the fact that the many consent management platforms that adopt this framework are not fully compliant with the requirements of GDPR. Basically, research indicates that cookie banners on websites often do not respect the choices of users. About half of the European websites violate the GDPR by installing profiling cookies before obtaining user consent. And it's very difficult to change or undo previously accepted settings. Lastly, manipulative techniques such as dark nudging and implicit consent are widespread. Our proposal aims to introduce an intermediary in the form of browser add-on between the user and the consent management platform within the transparency and consent framework. Essentially, the user expresses their preferences just once in the browser add-on. Then, whenever the user visits a website, the browser add-on automatically responds to the consent requests according to the policy of the user. The novelty of the proposed approach is the use of a large language model to generate and implement rules that enable automatic responses to consent requests. To describe our approach, we show a practical example using the Quancast website. Quancast is a company that provides several tools. A free tool called Quantacast Choice is used for managing consent. We assume that users want to reject all cookies. When a user visits the Quancast website for the first time, they see this banner. It's important to note that this banner encourages the users to accept all cookies by highlighting this button. To reject all cookies, the user must first click on the More Option buttons, and then he make 2 further clicks. We requested ChatGPT to generate rules for obtaining consent responses, locate buttons on the page, and generate the required code for the interaction. This is the sequence of questions asked to ChatGPT during the conversation. The first question provides the context for the entire conversation. One then asks for the position of the buttons used to indicate user choice. Finally, we generate the JavaScript code that interacts with the banner buttons based on the user's preferences. This is a simple demonstration of the final result. Once the browser add-on is installed, it will automatically reply to the banner on behalf of the user. Please note that this menu item has only been added for this demonstration to display the cookie banner before the script was called. In a real-world scenario, the browser extension interacts with the cookie banner after the page loads, without any user intervention. To recap, in our study, we introduced a framework to create rules for automatic consent based on the policy of a user. We enforce these policies with a browser add-on. Then, the use of a large language model ensures scalability and adaptability to customized cookie banner. In addition, by eliminating the user interaction with the cookie banners, we reduce the negative impact of deceptive design techniques that encourage users to accept all cookies. Lastly, we also saved users time by reducing the need to express their preferences on every website they visit. In our case study, we have shown that even rejecting all cookies can require up to 3 clicks on 2 different screens. That's all. Thank you for your attention.
Thank you very much for your presentation, and congratulations for the addressed the issue. Yes, I have a question. Do you think that is it possible to employ your solution not only for GDPR, General Data Problem Regulation, but also for other regulation and international regulation?
Yes, it could be extended also in a form of a personal manager information services that collect also other users' information and provide a response in behalf of the user.
Okay, thank you. Any question?
I have one.
Okay.
Please tell us about future works of your research paper.
Are you able?
No,
Are you
I
able
can't hear very well.
Please here. Come here.
Come here to the microphone.
Yes, the microphone.
Okay. You can tell something about future works, forecasting of future works for your paper.
Yes, there is the need to enable, find a way to standardize the mode in the kind of preferences that user can use. For example, this is a browser extension used for a specific browser, but we need an implementation that could be used for every browser and also in, for example, an operating system, in a PC, on a smartphone, to enable the personal information management system to interact also in other contexts, not only on websites that a user visits.
Okay, thank you very much. The next speaker could be Dr. Krishma, titled "Secure Mobile Ad hoc Routing Using Confrontation," but I think that is not present here. Okay, so thank you to all authors for their interesting contribute and their brilliant presentations. I hope you found this workshop a good content of ideas that have stimulated new research and applications. And I invite you to join in the next session. Okay, the workshop is end. Thank you very much to all.
Thank you.
Thank you.
Thank you.
Bye.
Thank you so much.
Bye.
Bye.
Ciao, ciao.
No?